Hi, my name is Nick Connolly. I'm the Chief Scientist at Data and the Chief Scientist and Chief Architect at Datacall Software. Can SPDK deliver high-performance NVMe on Windows? In this talk, I'll be covering some background, including the current state of NVMe on Windows and how this project came about. Then, looking at how we got started, the Windows Platform Development Kit that we built, the changes to upstream projects, and the current status. I'll cover some personal reflections on the lessons I've learned and tell you how you can get involved. Let's get started with some background. NVMe is a low overhead specification designed from the ground up to deliver high performance from today's SSDs. It's a replacement for the older SATA and SCSI interfaces with a limited command set for efficiency. I/O is issued through a command and response queue with a large queue depth, and multiple independent I/O queue pairs enable lock-free parallelism. NVMe over Fabrics extends that connection to a remote NVMe device over a transport protocol. The aim is to deliver near local performance with a target of less than about 10 microseconds of additional latency. At the moment, the main transports include InfiniBand, RDMA, Fiber Channel, which can run over existing infrastructure, and TCP. On Windows, using a directly connected NVMe disk is supported out of the box by the store NVMe.sys mini-port driver. It does a good job, but some vendors offer their own driver that's tailored specifically for their hardware. All of these, though, are kernel drivers, which means that every I/O involves crossing a protection boundary, which adds overhead. There is no native support for NVMe over Fabrics on Windows. Broadcom and Marvell offer drivers that work with their fiber channel adapters. There aren't any supported Mellanox drivers. And Starwind offer a software initiator that works with Rocky V2 or NVMe over TCP. And as far as I'm aware, that's about it. As Datacall's chief architect, I've spent many years building high-performance, low-latency storage stacks running in the Windows kernel. We've developed innovative multi-threading techniques to minimize contention in systems with tens to hundreds of cores. It's skilled work, it's time-consuming, and that makes it expensive. The multiple I/O queue pairs in NVMe provide a way to attain similar levels of parallelism at a much lower development cost. By dedicating a queue pair to a specific context, the need for locking can be eliminated, and deterministic I/O rates can be achieved, including directly from a user space process. One of the interesting technologies that has emerged in the last few years is the Storage Performance Development Kit. SPDK is a well-regarded set of tools and libraries for writing high-performance, scalable, user-mode storage applications on Linux and FreeBSD. It's cutting edge, leverages the latest NVMe features, and uses a poll mode with a lockless thread per core design. Production ready, portable, flexible, and open source with a permissive license. What's not to love about it? Data leads the development of OpenEBS, which is a CNCF sandbox project and the most popular open source storage for Kubernetes. We're using SPDK to build a new generation high performance storage stack designed from the ground up to be cloud native. It's at the heart of Data Enterprise Edition. As we were working on this, we realized that amid the flexibility and portability of SPDK, there's one small footnote that often goes unnoticed: not supported on Windows. It's understandable because much of the NVMe development has its roots in Linux or FreeBSD, but it overlooks the sheer scale of Windows Server deployments in enterprise environments. and thus was born the crazy idea, could we get SPDK to run on Windows? In some ways, figuring out where to start was one of the hardest parts of the project. It rapidly became apparent that this wasn't just going to be about implementing a few pieces of functionality. SPDK assumes a POSIX platform, which Windows doesn't provide. The build environment is based around make and shell scripts, which aren't native to Windows. There's platform-specific functionality that needs to be provided, and to add to the fun, there are several dependency projects with their own build processes. SPDK does include an environment library as a way of accommodating different platforms, but this isn't sufficient to provide all the support needed for Windows. It defaults to using DPDK, so that seemed like a good starting point. The data plane development kit is a set of libraries designed to accelerate packet processing workloads on a variety of CPU architectures running mostly in user space. By default, SPDK uses DPDK for memory management and to provide access to PCIe devices. As I researched DPDK, I came across references on the project's mailing list to a community working to add support for Windows. To find a community working on one of the building blocks needed to get SPDK running was a real encouragement. It was well established, with contributions from Microsoft, Intel, and NVIDIA, among others, and had already released an initial version in DPDK version 1905. I found the community to be friendly and approachable, so I got involved in the bi-weekly community meetings and attended the excellent DPDK Summit last year. At a time when we were all learning how to do virtual events, they really nailed it. And then after the summit, I had an excellent discussion with Dmitry Kozliuk, one of the key Windows maintainers. At this point, DPDK was switching to use Meson for builds, which is great because it runs natively on Windows. I remember a long weekend spent re-implementing all the SPDK build scripts to use Meson before realizing that it wasn't going to be the best route forward. And I'll say more about that later. In fact, setting up the build environment has been one of the biggest challenges, from choosing the toolset, GCC, Clang, Visual Studio, through to figuring out how to get a shell and install the required packages. We'd used Cygnus a few years ago, and it worked well, but there was always a bit of uncertainty about the extra layer that's involved. We wanted something that felt closer to a native solution. The initial work was based around supporting GCC, Mingy WW64, and Clang, and using MSys2 to provide a shell. But this is complex to set up and won't run the SPDK test suites because Python 3.8 doesn't include support for Unix sockets on Windows. The current recommendation is a Windows subsystem for Linux Type 1 installation using GCC as a cross-compiler, which produces native Windows binaries and allows the tests to run. Now that we've got a build environment, what are the design goals? Well, the goal was to get support for Windows integrated into SPDK rather than creating a fork, and that requires working with the community. When the project started, I'd been aware of SPDK for a few years, and I'd been to a summit, but beyond that, I had no relationship with the community. So figuring out whether changes would get accepted was a complete unknown. The smaller the better seemed like the best option. And that's not just due to the human factor. Changes introduce risk into a stable project. Having said that, my experiences with the SPDK community have been great. From my first exchanges with Ben Walker and Jim Harris, to being invited to talk to a community meeting about the project, code reviews on all the changes, through to ongoing exchanges with the core maintainers. I've found people have been supportive, inclusive, friendly, and responsive. Community meetings are effective, and there's an active Slack channel. I'd suggest if you have the opportunity, get involved. So we've got a build environment and a plan. Now, how do we make it a reality? The approach we've taken is to create a new project called the Windows Platform Development Kit, or WPDK, that provides a simple POSIX emulation layer targeted specifically at SPDK's needs. It implements a set of headers and a lightweight library that maps functionality as closely as possible to existing Windows semantics. The aim is to produce production quality executables that run as native Windows code. It's not intended to be a science project. There should be no surprises. As far as possible, the port should behave as expected without any hidden performance or functionality costs. It should be independently testable so that issues can be identified and fixed independently of the SPDK environment. Dependencies should be included for ease of use. For example, libcunit is required by the SPDK unit tests. It seems to be a dormant project, so WPDK includes a local fork of the repository with a few minor fixes in it. The code is licensed permissively to match SPDK. Here's an overview of some of the content. At the heart of WPDK is a set of include files. Windows is not a POSIX system and doesn't have POSIX compatible headers. Some files are simply missing. Some are present, but have missing definitions. And some need to be adjusted to handle compiler differences. In fact, handling multiple compilers correctly has taken a significant amount of time. Everything exported by WPDK library has a WPDK _ prefix to avoid namespace clashes. You can see in this example that getIFaddress is redefined to WPDK _ getIFaddress. Ideally, we'd do the mapping using static inline functions, but that can result in link issues if the symbol has been defined with DLL import. One of the areas where Windows differs from POSIX is error handling. Many of the functions that are similar will call an invalid parameter handler instead of returning enval. This needs to be explicitly overridden to ensure correct operation. Error codes also need to be mapped from Windows values onto the closest POSIX equivalent. There's no built-in POSIX thread support on Windows. There are some external packages available, but they all seemed more elaborate than was required. WPDK includes a simple wrapper around the Windows primitives to handle threads and synchronization types, such as mutexes, spin locks, barriers, and condition variables. There's also support for thread local values, affinity, and changing the thread name. POSIX includes an allocator for aligned memory regions, which is similar to Windows aligned malloc, but has one important difference. Free works with both aligned and unaligned memory, whereas Windows requires an explicit aligned _ free call. This means that WPDK has to wrap all malloc, calloc, realloc, and free calls, as well as anything that returns an allocated buffer, such as strudupe. The socket code in Windows is superficially close to Linux, but there are some significant differences. Most importantly, Windows returns an opaque socket handle, whereas POSIX uses standard integer file descriptors. To work correctly, all calls to functions such as read, write, and close need to be wrapped by WPDK. readv and writev are missing and need to be implemented using WSA receive and WSA send. There are also differences in behavior with non-blocking mode, and some of the socket options that need workarounds. The good news is that AF Unix is now supported between WSL1 and Windows, which means that the SPDK configuration calls will work. Windows has very limited signal handling. It's really just a way of handling exception conditions within the program. For example, signals can't be sent to other programs, and when you terminate a process, the sigterm handler doesn't get invoked. WPDK adds an event-based signal handling thread to receive signals and a WPDK kill executable to send them from the shell. This also allows for the graceful shutdown of processes when a termination is sent. There are lots more issues that WPDK resolves, from missing POSIX functionalities such as dirent, get time of day, mmap, poll, select, to missing libraries including UUID and crypto. In addition, WPDK provides implementations of Linux-specific functionality such as getifAddrs, epoll, and libaio. One of the trickier areas was adding support for GCC's mocking functions, which are used by the unit test code via the --wrap compile line argument. And finally, the ubiquitous issue running Linux code on Windows. There needs to be some form of path name mapping to keep everything sane. Let's take a look at what's been upstreamed into SPDK and DPDK. There weren't too many changes required to SPDK. The code is well written, well tested, and portable. The biggest issue was a difference in the size of basic integer types. Linux uses an LP64 model, where int is 32 bits, long and pointers are 64 bits. Windows uses LLP64, where int and long are both 32 bits and pointers are 64 bits. There are a few implications to this. Pointers won't fit into a long on Windows, and 64-bit values have to be printed with the PRI64 macros for portability. Many of the SPDK printfs assumed that %LX would be correctly sized. Fortunately, the compiler picked these up. In addition, a couple of the unit tests made assumptions about arithmetic limit values. On Linux, mutexes seem to work correctly, even if they're not initialized, but the WPDK implementation requires initialization, which caused several of the unit tests to fail. There was an issue where the Windows compiler handled the placement of bit fields slightly differently, easily fixed. A few if-defs needed fine-tuning to handle the Windows platform correctly. And combined with some minor adjustments to the build scripts, that was about it. A real testament to the quality of the SPDK code base. Very few changes were required to DPDK. There were a few build-related changes to fix warnings or settings. And the biggest change was extending support for mapping an Ethernet adapter into user space to also work with an NVMe disk. Is the project nearly complete? There's been a lot of work done, but there is more to do. We're currently at an alpha stage. Both the NVMe target and initiator run, and they can serve storage over NVMe TCP and drive I/O to a physical NVMe disk. I've seen a disk running at its maximum rated performance being driven by a single CPU core. For comparison, Iometer required 4 cores to drive the same level of I/O through the kernel. The code is also unit tested. All of the SPDK tests pass, and the majority of the WPDK code has unit tests. Conclusion. So can SPDK deliver high performance NVMe on Windows? Even in alpha? Yes, it can. As a newcomer to open source development, I thought I'd share some personal reflections to help others. Firstly, I've thoroughly enjoyed it. I've received a warm welcome and positive responses from both the SPDK and DPDK communities, and I'm very appreciative of that. I think partly that's because I set out to work with the community to find out where they were heading and get involved, rather than simply pursuing an agenda. And I've got a couple of examples of that. WPDK has a Windows layer, which I thought might be helpful to DPDK on Windows, but their goal is to have self-contained platform-independent code. It's not the approach I selected for SPDK, but it's a perfectly consistent option. In hindsight, it probably took me longer than it should have to realize this, but they were gracious. With SPDK, I spent time rewriting the build system in Meson, but I'm glad I didn't try and pursue this. After all, who wants a newcomer to a project proposing a complete replacement of their build system? I'd also suggest being patient. Projects may not always move as fast as you'd like, but they have their own agendas and release schedules, and people have other demands on their time. And be respectful. Remember you're a guest and don't dominate discussions to pursue your own agenda. But above all, have fun and create something worthwhile. Yes, you can get involved. Contributions are welcome and needed. Please head over to the WPDK documentation and WPDK repository to get started. Please also join the SPDK community and tell us how you're using SPDK on Windows. For real-time discussions, the SPDK Slack contains a Windows channel. Happy experimenting. Thank you for listening. Hopefully you found the content interesting, and I look forward to hearing questions in the Slack channel. I'd also like to thank Maya Data for their support and encouragement of this project. Thank you, and I look forward to seeing you at wpdk.github.io.